Hey guys, this is chapter 8 and 9 review, page 7. So kind of getting into the proof section here. When we first started proofs, we started with something that we were a little bit more familiar with, and that was solving algebraic equations. We want to start there because that's a little bit more familiar to us, and we know how to do it. We just wanted to figure out, how to justify the steps. So a justification has to be some kind of rule or property or theorem or postulate or definition or something that we've already established as true. So justification is not saying what you're doing, it's actually citing a specific property or idea that says I'm allowed to do this because this property says I can. So that's what we're going to do here. We're going to solve this equation with justification, which is, again, our intro to how to structure a proof. So the first thing is to just start with the given. Okay, now our last statement, I don't know exactly how many lines it's going to take, but this should be our last statement. That's what we want to get to. Okay. There's more than one way to solve this. You might solve it a different way or in a different order, and that's totally okay. One of the ways that you could solve this is to get rid of the fraction first by multiplying everything by 3. You can also, do it a different way, but probably what I would do here, just to make my life a little bit easier, is I would start by adding 2 to both sides. Again, that's not the first step that you have to take, but I think in this case that'll make it easy. Also, we're not going to show our work. Typically, if we were solving an equation, I would do +2, cross it out, +2, right, and that kind of thing. We're not going to do that, but I might do that down here just so you can see what I'm doing, but we wouldn't include that as part of our proof. So if you wanted to, you could solve this equation like on a separate spot, just so you make sure you're doing it right. So that's going to be this is going to be the next step. I'm going to add 2 to both sides. So my next statement will be 2x minus 5 equals 1 over 3 times x. And I added 2 to both sides, so that's the addition property of equality. Now you're welcome to abbreviate just like I did, but you have to be specific that this is a property, okay? So if you write add prop of equal, that's fine. What you don't want to write is addition, because addition is not a property. Addition, I mean, it is, but like if you say addition, I don't know whether you're citing a property or just saying I added. Okay, so addition, if you just say addition, it sounds like you're referring to an operation and not a property. So you have to state that this is a property that we're talking about, and it's the addition property of equality. Okay, the next thing that you could do here, there's a couple ways to do this, but I would probably just get rid of the fraction. That's what I would do in this case. I would multiply everything by 3 here to get rid of that fraction. Now you don't have to do that. You could, subtract 2x from both sides. If you do that, though, you're going to have to worry about common denominators, and that can get a little bit hairy. So this is what I would do. Down here, what I would do is I'd have 2x minus 5 equals 1 over 3, and I'd say, look, I'm going to multiply everything by 3 so that I can cancel out that 3. So we're going to do that, and we're not going to simplify just yet. We're going to do this in 2 steps, just to make it really clear. Okay, so what we're using is the multiplication property of equality. Abbreviation is fine, but we want to make sure that we're stating that this is a property. And also we need to say that it's a property of equality. So don't just say multiplication there, because multiplication, if you just say multiplication, you're not referring to a property. Okay. The next thing we're going to do here is we're actually going to distribute here. So what you'd have is you'd have 3 times 2x minus 3 times 5 okay, something like that. Sometimes you can combine some of these steps, but I want to kind of be explicit so you can see every step. So all I did was distribute. I didn't even multiply them yet. I just showed that this 3 was multiplying each of these pieces so that I can kind of say that just this one step, this is distribution. Distribution prop of multiplication. Remember, the distribution is not a property of equality, it's a property of multiplication. Okay, now that I've said that I'm distributing, or I'm showing that I'm distributing, now I'm actually going to like multiply it out. So 3 times 2x is 6x, and negative 3 times 5 is negative 15. And here, what you're going to get, basically you have 1 over 3 times x times 3, right? And so, actually let me do that down here. 1 over 3 times x times 3. So you can rearrange this and kind of, so you can see a little bit more what's happening. The 3's are going to cancel here, or in other words, if you go 1 times 3 is 3, 3 times 1 is 3, you get 3 over 3x. So either way you slice it, you're just going to get an x there. Okay. So since we're justifying our answers, but we're not really showing our work here, we're just going to have an x over here. So what we're doing is we're replacing 3 times 2x with what it's equal to. We're replacing negative 3 times 5 with what it's equal to. We're replacing 1/3 x times 3 with what it's equal to. And so when we replace something with what it's equal to, that's the substitution property of equality. Okay. All right, now we can combine like terms. Now you could have done this earlier. We could have grouped the x's earlier. Like we could have subtracted 2x from both sides, or subtracted 1/3 x from both sides. But again, that would require you to do common denominators, and I rather would clear the fraction. You also could have like cleared the fraction way up here. Like at this stage, stage 2, I could have multiplied everything by 3 up here to get rid of that 3 down there. So there's multiple ways to solve this. But I think this is the easiest one without messing up with common denominators and stuff. So what we're going to do, again, let's jump down here. We got 6x minus 15 equals x. So if I subtract x from both sides, I'm going to get 0 over here, which is not going to help me out. So what I'm going to do instead is I'm going to subtract 6x from both sides. So I get negative 15 equals negative 5x. And that would be the subtraction property of equality again. Okay. Next step, I got negative 15 equals negative 5x. So I'm going to divide both sides by negative 5, and I'm going to get 3 equals x. So we're going to have 3 equals x, and that's the division property of equality. Okay. Now, is this what I wanted to prove? Pretty much. But there's one more step, right? Now, it's pretty obvious to us that when you get to this point, you're just like, oh, well, x is equal to 3. It doesn't matter what order I write it in. But the reason why we know that, or what property we're using when we think that, is the symmetric property of equality, of the idea this is like I can switch the sides and it doesn't really matter. So our very last statement here, we'll have an extra line, that's okay, is x equals 3, and how we get that is the symmetric property of equality. Okay. If you have to add a line, that's fine. I didn't count out exactly how many lines each of these would take. I just kind of threw down 8 lines or whatever. So if you don't use all the lines, that's okay. If you use too many of the lines, or if you need to add a line, excuse me, that's fine. And like I said, there's more than one way to solve this. So if you want a different route, that's probably okay. Just make sure that you're justifying each step, and try to not do too many steps at once, because we want to make this really, really clear. The point is not to get the right answer. The point is to justify your reasoning and practice justify your reasoning. So if you're trying to combine a bunch of steps so that you can get to the right answer, you're kind of missing the point. The point is to show your deductive reasoning process. Okay. Let's do the next one. Number 42 on page 8. Alright, so these are 2 segment proofs, and I believe that both of these came from a homework assignment that you already did. So you could probably go back and just find that video. I believe it was segment proofs 2? I can't remember. I think it's segment proofs 2 for this one. I think this is on segment proofs 1. But anyway, let's go ahead and go through this. Let's see if we can understand what's happening first. So AY is congruent to XY. So these two segments are congruent. Okay, YZ is congruent to YB. Okay, so these are congruent to each other. And we want to show that this whole segment AB is congruent to this whole segment XZ. Well, just by looking at it, you're like, well, that's obvious. If these two guys are congruent to each other, and these two guys are congruent to each other, I'm just adding two equal pieces, so I should get two equal segments. And that's true, but again, the point of a proof is not to rush to the right answer. The point is to create like a rock solid case that nobody can refute. So it's an exercise in practicing deductive reasoning. So we don't want to rush it, and we don't want to be like, oh, it's obvious, right? We're going to prove this. Okay, so AY is congruent to XY, and YZ is congruent to YB. Okay, that's the given. Okay, now what we want to get at the very end is AB is congruent to XZ. I'm putting that way down here because I don't know how many lines I'm going to take, and I'm just going to give myself as many lines as possible. But one of the things that you can kind of think about is you think about a proof like a bridge. Okay, so you got this bridge, right? Or you need to build a bridge. You're here at the given, and you're trying to build this bridge all the way over to the statement you want to prove. Okay, so when you're building a bridge, you can go from one direction to the other, but you don't have to go in one direction. You can like build a little bit this way, and build a little bit this way, and build a little bit this way, build a little bit this way, and kind of meet in the middle. And so sometimes that's a good method for a proof, is to like start with your given and go forward, start with the statement you want to prove and try to work your way backwards a little bit. So we might use that strategy here. Whenever I see a congruent statement, usually the next statement I want to go to is an equality statement. And that's what we're going to do here. So our next statement is, well, if these guys are congruent, then that means their measures are equal to each other. So we're just going to build on this piece of information. Two segments are congruent. What does that mean? It means their measurements are equal. So this is the definition of congruent segments. We're going to abbreviate that def of cong. Now if you use that same reasoning and you're like down here and you're like, I want to say that two segments are congruent to each other. It kind of makes sense that maybe the step right before this was saying that their measures are equal. So this kind of gets us, like, if we can get to this step right here, then we can easily get to this step. So that's also going to be a definition of congruence. And notice how we're kind of building in from the ends. We just got to fill in the middle now. Okay. The next statement that we actually could make several statements here to get it going. There's different orders that we can order this proof in. But I think the one that makes the most sense is to start talking about where AB comes from. If we're trying to get AB in the final answer, then we need to start talking about AB. And right now we don't have AB. We have AY, and we have XY, and we have YZ and YB, but we don't have AB yet. Okay? Hold on, I feel like I'm missing something. Y, Z. Yeah, okay, sorry. So we need to actually come up with where AB comes from. We're gonna have to get to AB eventually. So what we're gonna do is we're gonna go AB equals, and we're just gonna look at AB. So how do we get AB from the pieces we have? Well, we have AY and we have YB and we have XY and YZ. So what we're gonna do is we're kind of gonna build this piece that we're gonna need later. So AB is equal to AY plus YB. And in the same statement, we can say something similar about XZ. Right? We know we're going to have an XZ eventually, so let's just build it and figure out what we can say it's equal to. So we know something about XZ, and what we know about it is it has to be XY plus YZ. And the reason we can say that is what we call the segment addition postulate. basically what we're saying is the whole segment, the measure of the whole segment has to equal the measure of the two segments that make it up. So postulates, again, are self-evident truths, so that's a pretty obvious idea. But notice we're building towards what we want to say. Okay? All right, let's think about this for just a second. Let's take another step backwards. Okay? If I want to say that AB is equal to XZ, then one of the things I could do is I could say, well, if we can show that AY plus YB is equal to XY plus YZ, then we could get there. Sorry, hold on a sec. I put this in the wrong spot. This is the justification for the last step. We're going to need that space right there. Okay. So the reason why I'm thinking this is because if I want AB equal to XZ, notice that AB is equal to this stuff. So AB can be replaced with this because AB is equal to that. And XZ can be replaced with this because XZ is equal to that, and vice versa. So if I can get to this step, then I can just say, oh, well, this can be replaced with AB, and this can be replaced with XZ. So that's maybe somewhere where I might want to go. So I'm kind of, again, taking a step backwards. So going from here to here, this would be a substitution prop of equality. If I can get these two things equal to each other, then I can get down here. Okay. This is where it gets a little bit tricky. Okay. What I got to do is I need to find AY plus YB. I need to figure out what that's equal to. So if we go back up here and we look, we see, oh, we have an AY, right? And I want not just AY, I want AY plus YB. And so what I can do, I'm going to go up here so this is a little bit clearer. If I have AY equals XY, this equality statement, what I can do is I can add YB to both sides. So it's just like adding 5 to both sides, or subtracting 10 from both sides, or dividing by 2 on both sides. If I add the same thing to both sides of an equation, it's still equal. Okay, so if I have AY plus YB, that has to equal XY plus YB. And what I'm doing here is I'm using the addition property of equality. I'm just adding the same thing to both sides. Why? Because I want to try to get a statement that has AY plus YB in it. That's where I'm headed. Okay. Now this almost matches this, so we're pretty dang close to finishing this up. The only thing is, how do we get from here down to here? Okay. This statement right here follows from this statement. AY is equal to XY, then AY plus YB is XY plus YB. Okay, now notice we only used half of this statement. This piece says that YB is equal to YZ, which means that we can replace YB with YZ. So I can go from this line to this line by just replacing YB with YZ. And we're allowed to do that because they're equal to each other. So this is the substitution property of equality. Okay, now I have an extra line in here that I actually didn't need because we can just go right from here to here. We didn't need that, but I just wanted to make sure that we were going to have enough room. So I wasn't sure exactly how many lines we were going to take. But now we got it. We figured it all out. So let's run through just forwards. Okay, the first thing we do is we start with the given. Then immediately change to congruence. So if we have a congruent statement, then we are going to be able to get an equality statement. Okay. From there, we actually build this. If we're talking about AB and XZ, we need to figure out what those are equal to in terms of the other angles that or the other segments that we're given. So we use the segment addition postulate to say AB is equal to those two little guys, and XZ is equal to the measure of those two little guys. Add it up, and that's where we get that. Okay. From there, we kind of build off of this piece of information. We just use the segment addition postulate. We take this statement right here and we just add to it. We add the same thing on both sides. We add YB on both sides. Okay, addition property of equality. Then we take this piece and we say, hold on a second. YB is equal to YZ, so I can replace this YB with YZ with another substitution property of with a substitution property of quality, excuse me. Okay, now that we have this, we can replace this statement with what it's equal to, AB, and we can replace this statement with what it's equal to, which is XZ. So this statement turns into AB, right? Because again, AY plus YB is the whole segment, and XY plus YZ is XZ, the whole thing. Then we just simply change it to congruence, back to congruence, and we've got the thing that we wanted to prove. Okay, so that's a little bit tricky, but this is not the first time we've seen this one, and I think this is maybe the second time we've seen this one. And some of these segment proofs are pretty similar to each other. They require similar justifications and steps and things like that, similar logic. So if you don't totally grasp that yet, I would try it a couple more times, cover these up, see if you can like remember what it says, and then if you can't, go back and look and see if that makes sense to you, and then cover it up again and see how far you can get. So study them out, try to understand that logic and where the pieces come in, and that will help you get ready for the test. Okay, this is going to be a similar proof but easier. So let's do it real quick, and then we'll end the video and we'll do the next page in another video. So same thing with segments, but this time they overlap, and that makes our life a little bit easier. We know PQ and RS are congruent. So this little guy here, PQ, is congruent to this little guy. And what we want to show is that PR, the segment from here to here, is congruent to QR, the segment from here to here, or sorry, QS, the segment from here to here. Which kind of makes sense, because if you start with two congruent segments and you add the segment to both of them, you're going to get congruent segments. So these are congruent, and to both of these we're going to add QR. So that's kind of the idea. But again, the point is not to just, brush through it or be like, oh, it's obvious. The point is to practice justification and practice logic and deductive reasoning. So let's start with our given. Okay, and I don't think this proof is going to take as many lines, so I'm just going to go down here and I'm going to put my last line. That may come back to bite me in the butt later, but I'm just going to assume we're going to have enough space here, because I'm going to try to bridge the gap here. I'm going to try to work from both ends. So this is given. I have no idea how I'm going to get here just yet. But the next statement I'm going to make is that PQ has to be equal to RS. Like the measurement of PQ. The measure of PQ is equal to the measure of RS. This is saying two segments are congruent. This is saying two measurements are equal. And again, that's definition of congruent segments, or def of con for short. Now if we're down here, if we're trying to get to here, we know we could get here if we knew the measure of segment PR is equal to the measure of QS. Then we know we could just easily get here by doing the definition of congruence. So that may or may not be our last statement, or second to last statement. In this case, I know it is, but that's just like a strategy for you to try and see if you can get there. If you can maybe get to like an easier step or a closer step. So we're just building this bridge from both ends. Okay. Notice that we have to talk about PR and we have to talk about QS somehow. And we don't have those segments yet. Our given is talking about these guys, these little short guys. So if I want to talk about these longer segments, I need to like build them, or I need to kind of like see what they're equal to. So let's talk about where where PR is going to come from. If I'm going to end up talking about PR, well, let's talk about how you get PR. PR is the sum of this measurement PQ and this measurement QR. Or I should say the measure of PR is the sum of the measure of PQ and the measure of QR. So PR is equal to PQ plus QR. And that's again the segment addition postulate. Now if we want to, we can kind of combine lines here. We'll use the same line and we'll say, well, let's talk about QS, because we're going to have to, the whole idea is we're trying to prove something about QS. So the measure of QS comes from the measure of QR plus the measure of RS. And that's, again, the segment addition postulate. Okay. What we already know is that PQ is equal to RS. So this PQ and this RS are similar to each other. So that's something we know. Sorry, I got stuck. Where is our next step? It's going to be a substitution. Okay, let's see if we can work backwards. Oh, I know. It's going to be the addition property of equality. That's what we're going to do. Let's take this statement right here. If I take this statement, I can add the same thing to both sides. So if I had x equals y, I'm allowed to do plus 5 plus 5. Right? That's legal. Okay. So let's go back and see what we need to do here. If I have PQ equals RS, what I can do is I'm allowed to go plus QR plus QR. That's legal. The reason why I want to do that is because I want to be able to say that these things are equal to each other so that I can say that these things are equal to each other. So I'm going to take this statement right here and I'm just going to add QR to both sides. So PQ plus QR is equal to RS plus QR. Or we could do QR plus RS if we wanted to. I think that's kind of the way we want to go. It doesn't really matter because addition is commutative, so the ordering doesn't matter, but if we write it in a specific order, that would kind of help us. Okay, so PQ equals RS, right? PQ RS. What we did was we added QR on both sides, and that's the addition property of equality. Okay. Now we can use our substitution. That's what we wanted to be able to do. So now that we have these two things are equal from this line, we can use this line to say, hold on a sec. PQ plus QR, that's just PR. QR plus RS, that's just QS. Right? QR plus RS, that's just QS. Okay? And then it looks like we have an extra line here. So this is the substitution property of equality. Okay, so this is just an extra line. We didn't need this. But we didn't know. We didn't know how many lines we were going to need, so that's fine. You could go back up and place this one up here if you want to, or whatever. Not a big deal. And we should say this is the substitution, not the subtraction, just so we're clear. Substitution. So the reason why that can be kind of hard sometimes is because this line right here, this doesn't have to come right here. We could swap the order of these two lines. You could have gone directly from this to this, and then put this one after that. So sometimes when you're doing a proof, like you're just gathering a bunch of information, and then later you're putting it all together. So this line follows from this line, and then this line follows from this line. And this line just kind of like is one you just got to kind of throw in and add somewhere. Whether that comes in on before or after doesn't matter. But you need both of those two lines to get this substitution. So the order, again, is not always a specific way. And that's why sometimes you can forget, like, what step do I do next? Once you have all the information you need, you can do that substitution. So if you did it differently, and I think when I actually originally did this on your homework assignment, I did it in a different order, and you could definitely switch the order of those two if you wanted to, and it would still be valid.